Okay, then we will go to the first talk of this afternoon. Our first speaker is Professor Michele Ceriotti, and he's from EPFL in Switzerland. He's a professor. Oh, hi, Stuart. And now Stuart is also here and says hello. And we
hello.
Directors, we welcome everybody to the meeting. Michele is currently a professor at EPFL, where he heads the Lab for Computational Science and Modeling. He obtained his PhD from in physics in ETH Zurich, and then he spent years in Oxford as a junior research fellow. He's won many awards, including the IBM Research Forschung Prize, the Volker-Heine Young Investigator Award, and ERC Starting Grant, a UPAP C10 Young Scientist Prize, and most recently, just this year, an ERC Consolidated Prize, who's on a very exciting trajectory. And the title of his talk is Physics-Inspired Machine Learning for Molecular Materials Modeling. That I turn it over to Michele.
Thanks so much for the overly kind introduction, and thanks everybody for connecting. Good morning or good evening, whatever time zone you're in. And so my talk is going to be about modeling of materials at the atomic scale, and in particular, how you can use machine learning to extend the reach of atomic scale modeling of materials. Before I get to the subject matter, I want to make sure to acknowledge properly the people who did run most of the calculations that I'm going to talk about. And I think they deserve particular praise because, as you will see, a lot of the results that I will present are very recent, over the past couple of years. And so, you know, this is our last picture together in January 2020, before the pandemic hit. And now we are slowly coming back to campus. We can't all be together at the same time, and we have to wear a mask, but finally things are getting back to normal. And even though this has been a tough period for everybody, as you will see, the members of my group have been working really hard, and I think that that I've been able to do some really, really nice results. So I don't think that I probably need to emphasize the general importance of materials, how transformative they can be, given that I'm part of an entire series of workshops on the transformative potential of materials design. But I want to start with an introduction to convince you of the importance of atomic scale modeling and the role that machine learning can play into it. And I want to start from kind of a historical perspective. And if you go back and you look at the very early papers in which people started using computers to model materials and matter at atomic scale, the general trend that you see is that people were using very simple physics-inspired functional forms to describe the interaction between atoms, so something like Coulombic interactions, dispersion, and perhaps some harmonic terms to describe atoms covalently bound to each other. And then the key goal of simulations was to explore emergent behavior of matter, for instance, studying phase transitions, collisions, equations of state, and so on and so forth. So simple interactions, modelistic, fitted to experiments, and then trying to extract understanding of the emergent behavior. And then a little bit later on, in the 60s and up until the 80s, there was some kind of quiet revolution in which people, first of all, computers became more powerful, but also people developed very efficient ways to approximate the solution of the quantum mechanical problem for the electrons. And this opened up the possibility, essentially, to model quantitatively the behavior of materials and molecules without relying on experiments to perform a fit and without relying on empirical functional forms to describe the structure property relations. So come to modern days and come to what I'm trying to do in this field, where things really get challenging is when you start asking yourself questions about real materials in realistic thermodynamic conditions, typically finite temperatures or in the presence of defects. And this is where essentially modeling the emergent physical behavior using a first principles predictive description of the interatomic potential and the properties at the atomic scale, that's where the real challenge lies. And this is because you don't only have to reach higher and higher levels of predictive accuracy in solving approximate forms of the Schrödinger equation, but you also need to sample fluctuations. Essentially, the macroscopic properties of a material are rarely entirely determined by an individual configuration of the nuclei Q, but require averaging over a large number of configurations distributed in a way that is consistent with the thermodynamic boundary conditions. So the joint problem of achieving accurate description of the energetics for a single configuration and sampling millions of these configurations is what really makes fully predictive materials modeling still a very hard challenge. And here you can see a few examples of the systems in which with tremendous efforts over the past 10 years, myself, but also others, take Jorno Gebauer for the properties of metals, have been trying to push the limits of atomistic simulations and first principle calculations to study defects in iron, to study the behavior of liquid water, to study phase transitions. What puts together all of these kind of simulations is the fact that you need to compute the properties of a configuration millions or hundreds of millions of times. And this is really where machine learning promises to play a huge role, because the idea behind the application of machine learning to this field is really to manage to sort of cheat and get the accuracy of first principle calculations without paying the price. Now, given that this sounds a little bit like a free lunch situation, let me go through a very brief introduction to what we really mean with machine learning in this field. So the general idea is manipulating atomic structures, be them snapshots of a crystal or individual molecules, and use them as the input of some kind of machine learning algorithm that you can use to perform very different tasks. So you can use it, for instance, to classify structures that are similar to each other, to build low-dimensional representations that help navigate the results of a high-throughput search or a screening of materials. So you can visualize them in a way that makes it much easier to extract an intuitive understanding of what's going on. But the task that we're going to focus most on today is the task of performing inference. So essentially training a machine learning model so that you can then provide a new structure and make a prediction about its properties. So the way this regression, this inference process works is basically a fitting problem. So the idea is that you create a functional form, y tilde, that approximates the properties of a structure A that you also have computed for a small training set. And essentially, the training process involves optimizing the parameters that enter the definition of y tilde so that they come as close as possible to the target values ya. And something that I want to stress here is that you will see very simple machine learning algorithms in my talk. So I will not focus so much on using very sophisticated regression techniques, because there is usually a trade-off between the complexity of the model and its transferability and robustness. And this is very important for this field because, contrary to, for instance, image recognition or natural language processing, we don't have unlimited supply of high-quality reference data. We typically still need to generate reference data, and we still need to run high-end quantum calculations to collect the YA to train on. And this means that we are almost never in the abundant data regime, which is why most of what you will see is actually based on either kernel regression or relatively shallow neural network schemes. So another concept that I want to introduce, because I will use it as a diagnostic of the behavior of a machine learning model, is that of learning curves. So essentially, the idea behind the construction of a learning curve is to repeat the process of training a model by basically exposing it to a certain number of training structures, determining the model parameters, and then using the fitted model to make predictions on a new set of configurations. And then, since for this test set you also compute the actual target value of the property, you can compare the prediction and the ground truth and compute an error. And this is a generalization error. So this is the error that the model makes when it does a prediction on a structure it has never seen before. So if you repeat the exercise of training the model and testing it on a validation set, what you obtain is a curve that ideally should go down, and in particular the slope of this curve, the learning rate, indicates how efficient your model is in translating additional information to a lower error in making a prediction on a new structure. I mentioned that I will not present particularly sophisticated models, and the reason is that I believe that there is a crucial ingredient in the application of machine learning to atomic scale systems, which is the problem of representation. Essentially, when you use atomic structures as the input of a machine learning model, you typically want to process the Cartesian coordinates of the atoms in a form that is more mathematically suited to the machine learning scheme. And from that point of view, I just want to mention the fact that when I speak about a representation, there are many different ways you can build a representation of an atomic configuration to be used in machine learning. So the simplest way would be to associate a vector of features, finite or infinite dimensional, to each structure. But you could also define a metric, a distance, a measure of similarity between structures, or you could also use a kernel that by and large you can regard as a scalar product between features, and either feature vectors, distances, or kernels can largely, sort of hand-wavingly, used interchangeably. Okay? So you will hear me speak about kernels and features rather interchangeably, but because they are. So why do I say, why do I consider the problem of representation so important? One kind of circular argument might be just to look at how much effort has been devoted to the problem in the atomistic machine learning community over the past 10 years. So this is from a recent review that we wrote, and we built some kind of a phylogenetic tree of representations, and each of the names, the acronyms that you see in gray as the leaves of the tree are pretty successful and pretty widely adopted frameworks to represent atomic structures. And the way we organize these representations on this phylogenetic tree is basically starting from Cartesian coordinates and showing how you get to each kind of representation through a series of different symmetrization steps. In fact, one of the results that we have achieved on a very fundamental level has been showing how all of the representation that you see here on the leaves of this tree are very closely related to each other. For those of you who have a little bit of familiarity with quantum chemistry, basically different representations can be regarded as a different choice of basis to represent the very same family of objects. And I'm gonna give you a very short introduction of how you can build these more abstract and general objects that underlie any of these representations. So why did people come up with 100 different frameworks that all do the same thing? Now, staying in this kind of zoological metaphor, I believe that the reason is that representations over the past 10 years have evolved, undergoing some kind of convergent evolution process in which the requirements that were imposed by trying to get machine learning models that were more efficient and accurate are pretty much always the same, and they basically reflect fundamental physical principles. So for starters, and this might sound trivial, but it's not, you want your mapping between a structure and the feature space to be complete or more rigorously injective. So if you want that if you have two structures that are distinct, they should be mapped to different points in feature space, because otherwise, no matter how sophisticated is your machine learning model, you will never be able to predict different properties for structures that are different. And what makes fulfilling this requirement far from trivial is the simultaneous request of symmetry. So you want a representation of a structure to be invariant to the permutation of the labels of the atoms, rigid rotations, or rigid translations. Why do you want to have these asymmetries implemented? Well, because the energy of a molecule doesn't change if you rigidly rotate it or translate it in space. And if you use as the input of your machine learning model representations that are symmetric, your model will be automatically symmetric without the need of doing any additional work. Third, you usually want your representation mapping to be smooth. Again, this is just physics. Typically, the structure property mappings are smooth, and you want this intermediate step to reflect the ultimate properties that you want your model to fulfill. And one last requirement, which is less obvious but very important, is that your features, by and large, should have an additive structure, meaning that the features associated with a structure should be, in some sense, a sum of features centered on each atom. Now, the reason why this is a good idea is a kind of a divide and conquer principle. So it's very common in the modeling and in the theory of materials to associate extensive properties of a material, the energy, for instance, to a sum of terms that are associated with the atoms. Now, these are not the same number associated to each hydrogen atom, but these are atom-centered contributions that only depend on the correlations between the position of the atoms in a local neighborhood around each atom. And actually, you can show that this requirement on the structure of the target property is reflected in a requirement in the structure of the features that you use to describe a configuration. And the reason why this locality principle is very important to get a transferable model is that it allows you essentially to learn your structure property relations on relatively simple systems and then be able to pull the pieces apart and put them together in a more complicated and perhaps more interesting form, so that you can really fulfill this ultimate goal of getting predictive modeling of emergent physical behavior. So how can you build representations that fulfill all of these desiderata? So the most obvious way to describe the structure of an atomic configuration is by specifying the coordinates of its atoms. And even though this is a very simple way of describing a structure that gives a complete description of where each atom lies in space, this is clearly not symmetric. If I swap the labels of these two carbon atoms, I would obtain a structure that is identical to the one that I started from, but the vector of Cartesian coordinates would now be different. And the machine learning model will have somehow to learn the fact that the properties are invariant with respect to these atom swaps. So the first step in the construction is to build a representation that is invariant to permutation of the atom labels. And one possible way to achieve this is to describe the structure as a density. So you essentially put a Gaussian or some kind of localized function centered on each atom, and you describe the entire structure, this low-dimensional material that I made up, as the sum of these Gaussians. And then you see that you have a description which is still complete. I can still recognize the position of the atoms by looking at the position of the peaks, but I have lost the information on whether this carbon atom is atom 1 or atom 10. However, this description is still not fully symmetric. If I change the origin of my reference system, this will become a different function of R. And again, my machine learning model would have to learn that this doesn't have an impact on the structure property relations. So the next step is symmetrizing over translations. And one way of achieving this is averaging essentially this description over the translation group. And to do this without losing too much information, what you actually need to do is evaluate this atom density in 2 points and average simultaneously this tensor product of the 2 densities. And the reason why I get into these gory details is that something very, very elegant happens here, which is the fact that the mere act of symmetrizing over translations leads to a description of the entire structure as a sum of contributions that are atom-centered. And each of these atom-centered contributions is still a density, and this essentially is because the convolution of 2 Gaussians is a Gaussian. And it's a density which is, however, centered on distances between atoms. And this makes sure that this description is invariant to rigid translations of the entire system. It is, however, not invariant to rotations of the system. So if I change the orientation of the reference system, these atom-centered descriptors will change. And so the next step is actually to, again, average over the rotation group to incorporate rotational invariance. And those of you who are a little bit familiar with statistical mechanics and the theory of liquids, they will recognize that this process of averaging over rotations in atom-centered density is essentially leading to an object that is equivalent to the pair correlation function, the structure factor of a scattering experiment from a liquid. So this descriptor of an atomic structure incorporates all the information on the pair correlation between its atoms. So you can also see how this is not a complete description. In diffraction language, we're losing the phase, and we are losing information on the relative orientation of different atoms. So actually, you can build a whole hierarchy of these representations that correspond to endpoint correlations of this fictitious atom density, and this is one possible way to build a systematically improvable hierarchy of descriptors that you can use for the purpose of machine learning. And something that I really like as a side product of this construction is that if you build the simplest possible model, a linear regression model, out of this family of descriptors, what you obtain is a model of your property that is just essentially, if you take the pair correlation descriptor, is basically a pair potential. So something which generalizes in a data-driven manner Coulomb interactions or some kind of short-range pair interactions. Now, up to this point, I have been talking about the problem of learning scalar properties. But actually, if you are interested in the properties of materials, many interesting materials have properties that are anisotropic. And so you might want to build machine learning models that are not only suitable for scalars, but also for learning vectors or tensors. And here the idea is that basically if you rigidly rotate a water molecule, the dipole moment associated with that water molecule should rotate in exactly the same way. The concept here is called equivariance, and in order to build a machine learning model that is naturally equivariant, you need to start from a description of your atoms that is itself equivariant. And here you can see an example of how this works in practice. So here I'm basically just describing a linear regression model in which I'm using descriptors that are enumerated by the index Q for a structure A. And what you can see here is that my descriptors have an additional index, alpha, that correspond to the x, y, and z coordinates of the dipole that I'm trying to predict. So if I rotate rigidly my structure, what will happen is that I will be computing the descriptors for this rotated molecule. And now if I can construct descriptors that rotate under, when I rotate the structure, they rotate just as under the action of a rotation matrix, my machine learning model will automatically perform this equivariant transformation that is essential to learn vectors in this case. And actually you can generalize this, and those of you who are interested, you can look at the papers, lots of angular momentum algebra, but basically you can generalize this to obtain a fully equivariant model that you can apply to the learning of tensors of arbitrary order, and this really relies on the transformation properties of spherical harmonics under the action of a continuous rotation. So what can you do with these? Well, for starters, you can learn properties that are tensors. And an example is the polarizability of molecules. And actually, this is kind of nice because you can try it for yourself. You can go to alphaml.org, you upload the coordinates of a small molecule, and it will give you a prediction of the polarization tensor for that molecule. And the tensorial nature of the model allows us to capture, for instance, the anisotropic behavior of the polarizability for conjugate systems, and ultimately gives us a model that, when extrapolating to larger systems, has a better accuracy than DFT. So we're training the model on couple cluster, so high-end wave function methods, and the machine learning model predictions are not only 1,000 times faster than DFT, but also a factor of almost 2 more accurate. So you can also do something way more complex than this. You can learn, for instance, the electron density. So you can compute the electron charge density around the molecule or around the crystal, decompose it in atom-centered contributions, and then decompose these atom-centered contributions on a basis of radial functions and spherical harmonics. And now the coefficients in this expansion will transform as spherical harmonics, and therefore, using this symmetry-adapted machine learning scheme, you can construct models that are very efficient and very transferable. And for instance, you can train them on small dimers of organic molecules and make predictions for large polypeptides in a way that scales completely linearly with the size of the system. I should also add that even though technically there are some challenges to tackle, the scheme that we're using is entirely transferable. You can use it for isolated molecules, but also for the condensed phase. And we have a paper in collaboration with Mariana Rossi in Hamburg, in which indeed we extend this machinery from molecules to the condensed phase. So something very, very recent, we put this on the archive last week, basically. You can even build a model of the electronic Hamiltonian. You can learn essentially the matrix elements of the Hamiltonian that describes the structure, the electronic structure of a molecule in an atom-centered basis. Now, I will not hide this is a nightmare of bookkeeping, or a true tour de force, because you need to decompose your Hamiltonian to reveal all the symmetries that it contains. So you need to take care of the Hermitian nature of the Hamiltonian matrix. You need to take care of the fact that blocks of the Hamiltonian transform like products of spherical harmonics, and so you need to decompose them. But what you gain by having a model that is fully equivariant to these basic continuous symmetries is that you also incorporate automatically all the special symmetries that your system might have. So you might know, one of the foundation pillars of molecular orbital theory in undergraduate theoretical chemistry is the notion of the effect of the symmetry of a molecule on the properties of the molecular orbitals. Essentially, symmetry introduces some structure in the electronic structure that is completely independent on the details of the physics. So, for instance, the degeneracy of energy levels, or the way energy levels that are degenerate are split by the application of perturbation, the Untitled theorem that is also relevant for impurities in solids. All of these are rooted in symmetry. And what is really nice is that this model implicitly knows about all of these symmetries, which means that we can take a matrix that we interpret as the Hamiltonian of benzene, and we fill it with random numbers, literally, randomly generated numbers. And the model just cannot learn this because this is inconsistent with the symmetry of the molecules. So when we make a prediction, we get a Hamiltonian which has a lot of structure that reflects the symmetry of benzene. And actually, when you look at the molecular orbitals that come from this predicted Hamiltonian, so the value of the energy is completely random, but the degeneracy of the energy levels is what, and the symmetry of the orbitals is what is dictated by molecular orbital theory. And this is also true, as I mentioned already, with what happens when you break the degeneracy between two energy levels by applying a deformation. So after having given you this pretty complete, even if fast overview of the fundamental work that we have been doing on the structure of the representations that underpin machine learning models of atomic systems, I just want to give you a taste of what you can achieve once you have these symmetry-adapted models, and how we are really on track with fulfilling this program of predicting from first principles emergent phenomena. So for starters, I want to tell you a little bit about the thermodynamics of water. So water, very important system, but also very challenging system. And one of the reasons why water is so challenging for modeling is the fact that it contains a lot of hydrogen, and hydrogen nuclei behave as quantum particles. So not only you need to treat the electrons in water quantum mechanically, but also the nuclei, which basically increases by a factor of at least 30 the cost of a simulation of water. And so what we did here was to perform, using a machine learning potential, all the thermodynamic sampling, so basically to ramp up the sampling quality ladder in the two-dimensional plot that I showed you at the beginning of my talk, so as to be able to compute the relative stability of different phases of water from first principles using high-level DFT reference energetics, and incorporating all of the finite temperatures, the defects, disorder, and quantum fluctuations. And the result of this is that we can predict with no experimental input the melting point of water with an accuracy of, with an error of less than 10 Kelvin. And we can also capture the difference in melting point between light and heavy water, which is an entirely quantum mechanical effect. And we can even detect the relative stability of hexagonal and cubic ice, which are known experimentally to be very, very close in free energy. So we know that the most stable form is hexagonal, because that's what makes snowflakes hexagonal, but there is a cubic form that is very close in free energy, and it's exceedingly difficult to differentiate the two with simulations. And thanks to the use of machine learning as a stepping stone, we can really nail this relative stability with an accuracy of a fraction of a millielectron volt per molecule. And then another advantage of modeling at the atomic scale is the fact that you can probe matter in exotic conditions. So for instance, you can try and investigate the phase diagram of hydrogen in conditions that are found inside giant planets. And this is something that people had been doing painstakingly using a combination of molecular dynamics and first principle calculations. Now, thanks to the use of machine learning models, these can be extended to size and length scales that were absolutely unprecedented, which really makes it possible to approach the thermodynamic limit and try to answer questions about more complicated systems. So for instance, you know, the center of the giant planets actually also contains helium and a lot of other stuff. And going forward, this machinery would really make it possible to answer questions about these systems using exclusively simulations. Another example, more towards the applicative side, is a very nice collaboration that I made with a colleague of mine, Professor Foncuberta, and her lab focuses on the growth of nanostructures based on 3-5 semiconductors. And one of the challenges that they have is that when they grow gallium arsenide nanowires with a 1-1-1 orientation, you have two possible polarities of the gallium arsenide surface, one in which you have gallium as the terminating layer and one in which you have arsenide as the terminating layer. And during the growth process, these two surfaces are in contact with a droplet of molten gallium. And it is not at all clear what is the microscopic mechanism that leads to the difference in the defect formation rate and in the growth rate of the two polarities. So what they had done was to do some very complicated TEM experiments to measure the structure of the molten gallium layer on top of the two surfaces. And the problem is that these are very hard experiments. You cannot do them at the temperature at which the growth happens. And you only get a two-dimensional slice of the density of gallium. So you do get that there is some structure in the molten phase close to the interface. You get that there is a difference between the two polarities, but you don't really understand what is the mechanism that leads to the difference in growth behavior. And so what we could do was to run long time and large scale simulations with a machine learning potential trained on DFT and investigate the three-dimensional ordering at the surface, which reveals that basically there is a difference in propensity of forming metastable structures with hexagonal stacking rather than cubic stacking on one of the two surface polarities. And this is probably one of the leading contributions to the difference in the growth mechanism. And actually, there is more to come. We now have a machine learning potential that can span the whole binary phase diagram between gallium and arsenic. And so we really hope to be able to look in much more detail into the questions that arise for the growth of gallium arsenide nanostructures. Another example of a good collaboration with an experimental group is my collaboration with the group of Lyndon Emsley. So they are experts in NMR, in solid-state NMR, and in particular in NMR crystallography. And as a matter of fact, NMR crystallography relies a lot on simulations because it's a very indirect technique. So you measure the chemical shieldings of nuclei in a crystal, and then you compare the measured shieldings with the ones that you compute for many different candidates of the structure that you're trying to determine. And then the structure for which you observe the lowest discrepancy is the one that likely is being observed in the experiment. So here again, we built a machine learning model now not to predict the stability, but to predict the chemical shieldings of the nuclei. And you can try it for yourself on shiftml.org. But the bottom line is that we reach the same accuracy as DFT. And so we can really accelerate thousands of times the process of crystal structure prediction based on NMR. And actually, you can also, once again, bring into the modeling the role of thermal and quantum fluctuations, which is something which would be completely prohibitive to do brute force with ab initio methods, but using machine learning as a stepping stone, we can really do this quite routinely. And every time we tried this, we saw that incorporating fluctuations brought the computed chemical shadings closer to the experimental values, and we also get a much better description of the temperature behavior of the shadings. Now, up until this point, I have really focused on success stories about machine learning, but I want also to tell you a little bit about the challenges ahead. And one clear challenge is testing the limits of this locality assumption. So there are fundamental reasons why you might want to use a local description of the interactions in matter, but the question is how local is local? And you can actually test these by building a collection of machine learning models. In this case, we are trying to predict the cohesive energy of some small organic molecules, and we artificially restrict the local environments to 2, 2.5, 3 angstrom, and so on. And now you really see the power of these learning curves diagnostics. So if you have a small training set, kind of counterintuitively, the most accurate model is the one with the shortest cutoff. And this is because covalent bonds are short-ranged in nature, and they make up a bulk of the cohesive energy of a molecule. However, if you have a large training set, the learning curve saturates just because it doesn't contain information on the longer range correlations that underlie hydrogen bonds, electrostatics, and so on. And then, of course, one thing that you can do to make the machine learning model more efficient is to combine descriptors built on different length scales to build some kind of multi-scale model, which, as perhaps one could have expected, functions better than any individual single-scale model. However, this idea, in my opinion, is bound to fail when it comes to electrostatics. This is actually one of my favorite examples from undergraduate solid-state chemistry, and it's basically when you try to compute the cohesive energy of an ionic crystal. And if you do this exercise, what you find is that not only this is very slowly convergent as you increase the range over which you sum interactions, but you converge to a different limit depending on whether you sum over spheres or over cubes. And this is, of course, a consequence of the extremely slow convergence of the electrostatic interaction. And this is reflected in the fact that when you try to predict something like the binding energy of two charged dimers using a local model, you can't predict any change as soon as the molecules get further apart than the cutoff distance of your descriptors. And the problem is that you see here, I need to go out to hundreds of angstrom before the interaction becomes negligible. So the idea that we have to tackle this problem is something where we already have some very promising results, is to build a representation that at the same time combines a local component with the correct asymptotic behavior in describing long-range interactions. And the idea with, okay, this is perhaps my own perception, but I find very elegant, is that we start from the same fictitious atom density that we use to describe local interactions, and we solve the Poisson equation for it. So basically, we compute a fictitious electrostatic potential associated with this density. And I want to stress this is an entirely fictitious potential. We have a different one depending on the chemical nature of the atoms. And then what we do is exactly as for the atom density, we symmetrize this object and we end up with an atom-centered description, which, however, responds to deformations in faraway atoms in a way that is consistent with the asymptotic behavior of electrostatics. And actually, this allows you to learn interactions between molecules, not only charged residues, but also all sorts of intermolecular interactions. And something that actually surprised me is that we can actually learn also something as subtle and delicate as the interaction between a molecule and a metallic surface, which is, of course, extremely polarizable system. Nevertheless, this model can capture the correct behavior of the interaction curve. So, looking a little bit forward, so in which directions I would like to move with all of these, something which is keeping us very busy at the moment is actually an effort to integrate this machine learning machinery with the general modeling stack. And this really starts from an integration at the software level. You want to have modular components that are interoperable with each other and also with the different electronic structure codes, molecular dynamic simulations, workflow managers, and so on and so forth. And the second aspect that we are really trying to push towards is the idea of having integrated models that don't give you only one property, but allow you to predict at the same time all the properties that would be accessible to a quantum calculation. And this is really powerful because it means that you can, for instance, compute entirely with first principles accuracy optical properties of your system. Here you're seeing the IR and Raman spectra of liquid water computed with first principle accuracy using both an interatomic potential and a model of the dielectric response that is fitted on first principle calculations. You can also do some very fancy things, such as, for instance, predicting the electronic contribution to the heat capacity of a material. Metals at high temperature have a contribution to the thermophysical properties that are due to electronic excitations, and no matter how accurate is your interatomic potential, you will never be able to capture these without an explicit description of the electrons. And now we can do this using a machine learning model for the electron density of states rather than by running additional electronic structure calculations. And just to show you some kind of a flashy example of what you can do with these integrated models, we were able to study the behavior of silicon at high pressure, not only following the structural transitions that happen in silicon, but also using a model of the density of electron states to say something about the conductivity, which is the observable, which is typically used in experiments to understand what's going on in, when you apply tremendous pressures onto your sample. And so to conclude, the message that I want to give is that I don't really see physics-based modeling and data-driven modeling as conflicting, but I actually see an increasingly common trend in using these two together and to sort of incorporate some data-driven concepts, such as the possibility of accelerating the prediction of quantities that would be very, very hard to systematically compute with the electronic structure calculations, the possibility of analyzing the outcomes of simulations in an advanced way, but also there is a great promise in bringing concepts from physics, symmetry, locality, the presence of scaling and conservation laws into the construction of the machine learning models. And I really see the intersection between these two paradigms of modeling, the potential to build simulations that tackle once and for all these ultimate goal of being able to describe emergent behavior in materials in a completely first principles way. So without having to recourse to experimental data to verify and to pin the, well, there probably will always be a need for verification, but you don't need to use experiments to fit your model too, and you can really start from the first principles of physics and make truly predictive modeling, not just for idealized systems, but for the real deal. And with this, if you want to download the slides, I have put them accessible to everybody. And there is this review in which we kind of summarize some of the concepts that I've discussed. And if you have any questions, I will be very happy to answer them.
Thank you for the excellent talk, Michele. Are there any questions? Is there any on the chat? Not yet. Maybe I'll kick off with some questions myself. Can you give us a sense of how large your training data set is, or sets typically are, and where do you get these training data sets?
Those are both excellent questions. So if you choose your training data wisely, it doesn't need to be huge. So the model that we used, for instance, to model water, I think that there are a couple of thousand structures in it. We use both energies and forces, which helps a lot. But you can basically model at least a portion of the phase diagram of water with just a few thousand structures. Now, how do you get these 1,000 structures? Typically, what we are more and more often doing is some kind of active learning framework in which we start with a first guess that could be done with some cheap semi-empirical model. So we collect a few structures with a cheap model, we train a machine learning scheme on it, and then, even though I didn't have time to discuss this, we have pretty sophisticated schemes for uncertainty quantification. So we can just start running the calculation that we want to run, and we every time we get a large prediction for the uncertainty, we basically compute a new electronic structure calculation.
Thanks. So I'll move to a question from chat first, and then I'll go to Xin Lang after. So in the chat from a PhD student, she asked, what about topological transport? Could you model similarly and spin transport?
So this is an excellent question that actually goes really in the direction of making all sorts of electronic structure properties accessible to modeling. So what I find and what I believe is that in many cases, when you want to access electronic structure properties, it's more convenient to take an indirect route. So, and this is why, for instance, we are building models for the Hamiltonians or the electron density or the electron density of states. We really want to be able to predict the intermediates that then make it possible to compute the more sophisticated properties such as band structure, spin transport, that are really difficult to formulate properly as a direct learning problem.
Thank you. Then we go to Xin Lang.
Yes, okay. So Michele, thank you for the very interesting talk. So I think I heard some back voice from the lecture.
Yeah, there is a little. No worries.
Yes. Okay. So so my question is more going to the chemistry side. So have you ever used your machine learning approach, to predict some new reactions, especially more complex structures and the reaction are involved? And I'm questioning also, how is this your approach be useful to discover some new reactivities, based on the organic polymer reactions? I don't know how you can this keep it relevant for your research,
Yeah. So the problem of reactivity is very, very relevant, because even though there is now more and more attention to the high energy part of the potential energy landscape, particularly for chemical models, most of the early efforts have been targeting more or less ground state structures. And it is true that as you increase the energy range, the difficulty of the modeling becomes much, much larger, because this is just a fitting, okay? This is just glorified fitting. So as the dimensionality of your problem grows, you need more data, and there is very little you can do to avoid that. So one of the approaches that we are following to make it possible to model complex reactions, and for instance, we have a paper in which we model the regioselective oxidation of phenol. So it's a complicated reactivity in solution with explicit modeling of the solution. So the strategy that we take is very pragmatic. So basically we use a semi-empirical model as a baseline. And this allows you to get much more robust models that are accurate and robust even as your system undergoes a chemical transition. Now, there is a related question, which is the fact that also electronic structure methods tend to really be very, not so accurate when, apologies for the, so not so accurate when it comes to predicting chemical reactivity. And this is really where you want your machine learning model to be as transferable as possible, because then you can train it.
No, you should unmute. I think you are on mute now.
Yourself, yeah.
When did I mute? I didn't really click mute, so it must have been decided by Zoom.
Okay,
so yeah, I was. Where did you stop hearing me?
No, just last 2 sentences, I think.
Yeah, basically, yeah, we are basically trying to use semi-empirical models as a baseline to basically get sooner. I think that direct machine learning will get there, but I also think that a stepwise approach in which you start using some tricks to get there faster will also really help a lot. Getting to the point where we can make useful predictions sooner. And I think we are already at the point where we can make very useful predictions.
Okay, maybe just another small question, because you show an example about the NMR crystallography for the molecules that you predict the different peaks. I don't know when you in your approach, do you also consider the the more complex molecule structures which may involve the different solvents, solvent molecule interactions, the aggregation of the molecule in solution. So are all these factors considered during your modeling?
So this is an excellent question, and it's very conceptual. So I will try to give you a complete answer. So the short question is that we focused on do you hear me? Because I have a bit of a hard time hearing you. Okay, so we focused on solid-state NMR because in solid-state NMR is not such a bad approximation to consider the minimum energy structure of a crystal as an approximation of what is seen in an NMR experiment. Now, if you want to do this in solution, there is a conceptual challenge, which is the fact that the solution NMR experiment doesn't see the behavior of one specific configuration of your system, but sees an average of the different conformers that are explored during the dynamics. And so for that, it's really necessary to change the conceptual framework. So either you do molecular dynamics simulation of your molecule in solvent, which would be the most straightforward way, or you need to define descriptors that are not descriptors of individual configuration, but are descriptors of an ensemble of configuration. So this is something that I'm actually working on as part of my ERC grant, and it's a conceptual problem. It's not just a technical problem.
Okay. Okay, great. Thank you.
Thank you. So, are there any more questions? Speaker? And if there are none, then thank you very much again, Michele.
Thanks a lot. And now we go check out on what's the cause of this meltdown in the background.
Yeah, I don't know. Yeah, maybe it's from here. Anyway, we will also mute ourselves now.
No. It's definitely from here. I have to go and check why.
Okay.